Good. So let's start with very basic things. How do we make an amplifier, an analog amplifier? What you would typically do is look at the small signal model over here. So on the top left, we have our simple amplifier. This is designed to be a voltage amplifier. So that's the reason why I have a bias current over here. You draw the equivalent small signal model of an amplifier. For simplicity, I've omitted the gate drain capacitance here. And then we see that the gain is high at low frequencies, and it's very simple. Well, the gain goes down as we go to higher frequencies. And you could use this transistor up to a frequency equal to Gm over 2 pi, the capacitance at the drain side. If you want to have more gain at high frequencies, what do? Well, very simplistic approach. You tune out the capacitors. You make a resonant amplifier, not a broadband amplifier anymore. You put an inductor at the drain, you put an inductor at the gate to tune out respectively the drain capacitance and the gate capacitance, and you have a tuned amplifier. And if I assume that I can implement ideal inductors and extremely small inductors, then actually all of a sudden there seems to be no frequency limitation anymore of this circuit. And that means something is wrong, of course. What's wrong? Well, the transistor model that we typically use for analog design, it is way too simplistic. It's simplistic with respect to capacitors, yes, but what's more important is that it's too simplistic with respect to resistors. Because if you tune out the capacitors, what you will start to see are the resistors. So we have to develop a transistor model where we include the influence of resistors. Because if there is a parasitic capacitance that I under or overestimated, well, it just means I need to change a little bit my matching network and I tune out the capacitor again. So that means that we have to have a proper look at the resistors of the model. And to some extent, this is taken care of by the modeling people, and this is available in your PDK. But nevertheless, it is important now to understand how do these resistors scale with the size of the transistor. And that's going to be a big topic of today's lecture. In practice, there are different approaches. Either you have a very complex model based on measurements for a set of different transistor sizes. What's more commonly done is that you start with an intrinsic model here, and then afterwards you back annotate the parasitics, but you can only do that after you have drawn a preliminary layout or some sort of layout, and then you do a PEX, a parasitic extraction of that layout, and the parasitics are then added and so on. So this definitely makes the flow a little bit more complicated. But nevertheless, for our hand calculations and for our reasonings, and in order to understand should we make transistors large or small, for that goal, the simple model that I've drawn here at the bottom is more than sufficient. Of course, it's not sufficient to do accurate simulations, but the accurate simulations are taken care of by a complex in the PDK. But for our hand calculations and for our reasonings, the one at the bottom is sufficient. And so that's also the one that I will use today. So what is now limiting the gain? Because we started off with reasoning, let's add inductors, inductor at the input, inductor at the output, and then I have the GM RDS gain, and the small signal gain of the transistor all the way up to high frequencies if you want. So, but what is limiting? Well, the first big limitation is coming from gate resistance. So the gate electrode itself, the material from the gate, has some physical resistance. And that resistance creates a low pass filter. I have an RC filter over here. And in a simplistic approximation, you can say that the transistor itself reacts to this gate source voltage. And now you see that you cannot tune out the gate source capacitance. We cannot connect an inductor over here. We can only connect a component at that point. And so you always have a low pass filter at the input. As a matter of fact, the same is happening at the output, and there is also some source resistance, and that's also important. But in most of the cases, the gate resistance is really the limiting factor for gain. That's the first limitation. The second limitation has actually nothing to do with resistors. It has to do with stability. In quite a lot of cases, we see a limitation of the maximum gain that we can get from a transistor, not coming from the resistors, but coming from the fact that if you try to achieve a high amount of gain, you end up with an oscillator. And so that's also something that we will explore today. If you do complex conjugate matching at the input and at the output, you have a stability problem. And so then the limit of gain is the stability.